Recording? Cool. All right. All right. So stress transformations. Yeah, these were covered in. Let me get rid of this thing. We talked about these in Emily mixed solids, and I'm sure they were at least like glazed across in some other mixed solids. But so at least for me, this is like a pretty darn confusing subject, like 2 and whatever years ago, and it is. I don't know, it's one of those things that's really hard to put into context, but also important at the same time. So it's like the way I think about it is like it's a stepping stone between like basic beam bending stuff and like more advanced failure theory and stuff like that. So yeah, of course, before we dive into that super deep, we want to check in about homework. So how was it? We can have a little chat about that. How'd it go? How'd it feel? Generally. Also, a reminder, there's a feedback form. If you ever want to like put anonymous feedback, you can put it there too. Yeah.
It's also worth saying, just because it was said multiple times, like last week, that like a reminder, homework is graded on the like complete incomplete scale, meaning that like if you submit something on time, made a genuine effort to it, like that, like you cross your bar for like incomplete. For complete, you need to have like the correct answers in units, and if you have any assumptions or anything like that, like written out, like if you solve the problem correctly, you get to the right answer and have the right units. That's going to be a good and complete. But if you're not there, what we're hoping to do is that within a week and a half of when homework goes out, or when homework is due, like you'll have your grade, and like there's unlimited reattempts. So like you can go to office hours, solutions, like the CAs will have the solutions, and everyone's there. Those will be posted. But yeah, just a reminder, like it should be short, and like if you really don't know, just write something down and then submit it anyways.
Goal is always learning, not like counting points out of you. No. Everybody good? No other feedback on homework for now? Cool. All right. Stress elements. So yeah, like I was saying, these are kind of an important stepping stone between like your basic like hand calculations and getting to actual like failure theory and stuff like that. So yeah, we're going to start with a really nice little red beam under load. So there's a tension load and a upward lifting load, so that causes shear in the beam, right? So there's tension and shear in the beam at the same time. Yeah. So like for the last couple of weeks, like for example, the beam bending and stuff like that, you would basically make a vertical slice, right? And take a chunk out of it and then inspect what happens at either of those two surfaces. Another way of getting answers that it's like, you understand why you would do this towards the end of the lecture today, I think, hopefully. But another alternative, like another way of looking at what's happening in a very particular spot on the beam is by looking at a stress element within that beam. So hence the small square there. So that's gonna be our stress element. So we're gonna zoom in on that real quick. So here's our stress element. And you can see those forces carry over. So that tension force and that shear force both carry over into that stress element. Does that make sense? So we're basically looking at a tiny beam within the big beam. And the important thing is the stress elements are, I don't know, people never really describe their size other than the word of infinitesimal. So like basically like zero width, but there are applications in which you want some width. So we'll get to that on Thursday. Yeah, basically super small. So like basically negligible like distances basically. So just we're looking at basically a pinpoint. So it's basically like the way I kind of think of it is like, it's like a finite element, right? So you're just like one very small section of a larger piece. So you can use it at different locations to find different answers. So in order to, because this whole system is in equilibrium, like beam bending, we're seeing it's a static problem, right? So in order to balance this, we need to add equal and opposite forces on the other side. So now the forces are balanced, but we have a force couple, right? And so in order to get rid of that, right now it's about to fly off the page and spin off like a helicopter. So in order to balance that, you have to add the other two shear forces. That makes sense? And then the other two possible things, this would be the loading in our case for the little beam, but the other two possible are the normal stresses in the vertical direction. So basically the blue stresses are normal stresses. So, like always, these are the same stress, right? Like these are the same thing acting in the opposite direction of this part pulling it, right? And then this is also the same force, right? Going this direction. So it's basically one and the same. So basically in stress elements, it's not even really thought of. I mean, so this is like basically a free body diagram, right? For this tiny square. It's not usually thought of that way. I don't know. It's really weird. All the stress element stuff and stress transformation stuff is all like very abstracted away from normal mechanics. So I'm trying to like ground it in something that's kind of funky. Yeah, and then you have these 4 areas, which are all the same value, right? So, and that's all your shear stress. And so basically the 2D state of stress for this body is given by this matrix right there. Yeah, we're not going to do any kind of matrix stuff today, but we might on Thursday. We'll see. Yeah, and then of course you have to like the really important thing with this, you have to define your coordinate system because everything starts getting weird and changing. Yeah.
Real fast, does everyone understand how the subscript works on shear stress and how you label which one you're thinking about? No? Do you mind?
Go for it. Yeah, go for it. Absolutely.
So this was super confusing for me for a long time. In some cases, you can get away with it of just saying like, oh, they're just going to be equal to each other. The way that we do it, so if I grab that 2D stress element, and again, as Nathan said, critical that you actually label out your coordinates here. The way that it works is that when I have shear stress acting on this face, first I start with tau, that just starts with shear stress. The first subscript denotes like which direction, like I'm going to find out what the next thing is normal to. So X means that I'm going to have one face or direction that I'm going in the normal direction of that of. So if I wanted to do tau XY, I have 2 options here. Basically, like like remembering right hand rule, I have 2 options where I'm sticking in this direction. I can either go in the Y direction, or a little confusing to write it this way, that's a big option, or I can go in the Z direction. And so what the second subscript notice is which direction my shear stress is actually facing. So like the first one denotes which face the force is going to be normal to, and then the Y or the second subscript denotes which direction that's going in. Because that confused me for a while, and I'll be honest, I didn't like fully get it until last year.
So in this example, then this would be XY and this would be YX, right? Is that right, Carlos?
Yes. And then
but they're equal.
yes.
Yeah.
In 2D stress states, we mark them as equal.
Yeah. Yeah. Anything that has the same pair should be equal, right?
Yeah. Yeah.
Even no matter the order. Yeah. Yeah. Okay. Yeah. And apparently, like I was watching a video and they said that there's like there's one video I found of a lecture that said that there's a time in which they would not be equal. I'm not exactly sure that would be, but that was very mysterious. I have not figured out what that is.
For most static cases, they're going to be.
Yes. Don't worry about it.
What was the bottom one?
So the bottom one is the same. It would be YX, but it's the opposite direction. But yeah, so that's a good thing to note, actually. The sign convention, this is the sign convention. So, oh my gosh, the bouncing sprites. Yeah, so this is positive, this is positive, this is positive, this is positive. So, if your shear is going this way, that would be negative. That makes sense. Yeah. So that's just like the arbitrary sign convention that's used to, if everybody, as long as everybody uses that, everything plays nice and makes sense. Yeah. And so, yeah.
Wait, sorry, go back.
Yeah.
On the bottom right, so it's not bottom right.
Both of the bonds on the bottom right are positive. Both of the shear stress are positive. Cool. Okay, so here is kind of the classic example that people like to use to put shear stress or stress elements and stress transformations into context. So kind of the classic thing is to have 2 beams that are connected together, loaded in tension with an angled bond or weld or some kind of a connection between the 2 at an angle that has different mechanical properties. So like, weld has different mechanical properties, of course, because it changes the heat treat, basically, like, changes that. Like it could also be like epoxy or it's basically some kind of bond that or welds that has different mechanical properties to the other 2 parts of the beam. And that is at some angle theta to, right, from vertical. So in this case, it's 20 something degrees. So in order to find the state of stress at that location, we're going to use a stress element. So we're going to put a stress element right along that break. And then we're going to rotate it. And we're going to transform the stress from this coordinate system, the coordinate system that aligns with that weld. And that will allow us to find basically the normal and shear stress along that weld. That makes sense? So the reason you can't just like take the components is it means it won't tell you about the shear. It'll tell you about the normal stresses at the joint, but it won't tell you about the shear at that joint. So you can't just like take the components of the force, if that makes sense. So that's why this is key. So yeah, so in our case, we're gonna have, these are our coordinate systems. So there's different ways people like to do this, but generally the way that I like the most is y prime and x prime. There's also like n and t, like normal and tangent, like, I don't know, there's different ways of doing it, different people use, but x prime, y prime is the way I kind of like. So yeah, so all we're gonna do is we're gonna take our stress element and then rotate it by the angle theta. And then we're going to use some equations to calculate what those new stresses are based off of these stresses. Behold, these are the stress transformation equations. Yeah, these are super key and important. If you want to, I'd probably like take a screenshot, just like screenshot these and put them in your notes, something like that, or write them down if you really feel like it. But these are like the big main key ones for the first part here. They're gonna be on the next couple slides too. So you don't necessarily have to copy them all down, but yeah, be aware that these are here. There's also a formula at the end of this slide deck. There's a formula sheet that has all the equations from today. There's a lot of equations. Next class, we're going to show you guys a way that's a little easier without, like, well, not easier, just less equations. Yeah, there are all the equations are listed at the end of the slide deck too. Yeah, basically, so if you look at the top, you have the normal stress in the x prime direction. So that would be this arrow right here. And so basically, it's a function of the normal stresses and the shear stress from your original coordinate system, and a function of the angle at which you rotate it. And that will, it's basically I wasn't not gonna do the derivation today, but the derivation is basically just trigonometric identities. Convert, like, you know, going through little hoops to basically convert it from these vectors to those vectors, if that makes sense.
You will do that in slides.
Yeah. Yeah, and then the y prime direction is the same thing, just moved around. So you can see this, just basically the two signs are flipped. The other thing you can do is you can add 90 degrees to theta, but you got to be careful about that with order operations, because you got to add it before you multiply by 2, or you just add 180 to it. But yeah, basically you're just looking at, you know, that direction versus that direction. So, and then the last one is the shear stress, right? So same basic principle. So, yeah. Any questions so far? That makes sense. Cool. Okay, I'm gonna add some numbers to this now. So arbitrarily defined that like tension load is 1,000 pounds, and decided to find our little bar as 1 by 1. So it's really convenient because it's basically 1,000 pounds per square inch of load, or 1 KSI. And I defined our angle theta at 25 degrees. So if you guys would like to do your first transformation problem, I can have you guys just run these numbers through. My favorite way to do this is Desmos, probably, just because it's easy to see. But feel free to choose whatever you want. Desmos is all. Yeah, and then yeah, go ahead and calculate these values, and we'll see if you guys get. We'll compare.
Is all the equations in the last slide here as well?
Yeah.
I didn't catch it.
Wait, what did you say? Oh yeah, yeah.
Oh, okay.
Yeah, I didn't put the load on there.
I can.
Yeah.
Might be better on the chocolate or something.
Yeah, there's a chart.
Right there.
Everything you should need should be on the next slide, though. But yeah. It's -25. Cool. Okay, you shouldn't necessarily need anything from the previous slide because it's kind of translated for you here. So yeah, so basically from the previous slide, that the original orientation of the stress element is going to be, there's nothing pulling it in the vertical direction, right? Because we're in the middle of the beam, there's no forces up and down in the middle, so there's no there's no y normal stress, and there's no shear stress because we're in pure tension, and so our x component is going to be 1 KSI. That should be everything to calculate. Also, feel free to chat. Or ask questions.
So like sigma x.
Yeah.
Is just the side on the right and not the like balancing sigma x on the other side.
Yeah, so there's only one segment. That's the weird thing at stress transformations. There's only one force, basically. There's only, these are equal and opposite forces to keep in equilibrium.
Yeah.
So, but the tension is just the tension on one side. Like
Okay.
that like this load is just this load, and this load is just to balance that load, but it's all the same load.
Okay. Which is that one on the left, like the other like normal stress, the x and balance will also be the KSI.
It's the same 1 KSI.
Okay.
Yeah, I mean, it's just like a beam bending problem, right? Where it's fixed on one side and there's a tension pulling on the other side. It's not two separate forces, so you're not doubling it. It's just one is resisting the other.
Okay, so-
Yeah.
So you could technically like solve the problem from the other side. Like, it's
Yeah, I
just
mean, yeah,
bigger.
you can you can move this label over here and it means the exact same thing. Which means if you rotate the stress element 180 degrees, you'll end up with the exact same thing you started with. Which is why that theta is 2 theta in all of the equations.
More circle.
More circle. Oh. I really like more circle.
Circle. That's a great one. Photoshop. Maybe not the most sensitive one.
All right, how's everybody doing? Everybody have an idea? It's making sense, everyone. Cool. All right, ready to compare answers?
Why is the magnitude actually different? Like, if
Magnitude.
you rotate the thing, is it still just the same?
Okay, well, think about the first thing is think about vectors, right? So like if you have a vector this way and you split it into components this way, the magnitude just are gonna, those are
I
gonna
see.
change, right? Yeah.
Component.
Well, kind of. So the normal stresses kind of break into components, but the shear stresses are different, and the way they interact is more complicated than just components.
Okay. So we're finding the x component of
The x prime component.
x prime component of, so the sigma y prime is not. Oh,
These are the ones I got. I did not pull this problem from a book. I made this one up, so that could possibly be wrong, but I'm open to hearing a contending theory. But you agree?
Can I jump in for a room? So you're 100% right. The magnitude is not changing. And like why stress transformations are useful is that we're not changing the load in any way. We're changing our understanding of the load and why we might want to look at it differently. So like, I don't want to spoil anything, but like, next week, we're gonna get into failure theories. And some materials will fail like in tension more, some materials will fail in shear more and stuff like that. And the idea is that when you rotate your stress elements, you can get information of like, okay, I'm going to be under the most shear in this direction, so I'm likely to fail in this direction.
So yeah, thank you. The overall state of stress hasn't changed. So the loading hasn't changed, and then the actual part hasn't changed, just the orientation of our angle of view has changed. So these are equivalent stress states, but it's just a different orientation.
But how do we just like spawn in a Y component when there is no Y component on that side?
Well, that is basically like a component vector, right? So if you have a like a vector pointing straight in this direction, these are the same thing as adding these two vectors together, right?
Yeah, okay, that is.
And then the shear appears because now we're pulling, instead of like pulling on the face of a square, we're pulling on it slightly sideways, right? So it's going to start stretching in this direction.
Right.
So there's kind of a trade-off that happens between shear and normal stresses as you rotate, if that makes sense. We'll see kind of a visualization of that in a few minutes here.
Okay,
Yeah.
that makes much more sense.
Cool, awesome. So yeah, one more plug and chug problem. This is why I like using Desmos, because you can just like change the numbers and updates. So this one is basically the same kind of thing. That's super annoying, except it has a Y stress also. And so we're gonna start with this problem here, and then we're gonna circle back to it to look at a little bit later. So if you guys want to calculate this out and see if this is also the that you get to. Yeah. Doing this by the equation method, which we're doing today, is pretty just kind of plug and chug. There's a few exceptions, but yeah. Yeah, so basically the same exact thing, except theta is now positive 20 degrees and there's a Y load now.
Don't ruin Chrissy's mom. Just like, he derives it in class. It's like,
Yeah.
In this case, so I'm thinking about the seam or the bond or whatever.
Right.
Does the stress element have to be sort of the same size with the bond?
So the stress element is infinitesimal, right? So it just, as long as it's where the bond is, it's going to be in the bond. So
But
yeah.
the bond material is probably, like, the bond material shouldn't really matter where the orientation of the stress element. You're really trying to figure out like on the actual seam, right?
right. So the orientation, right, like you said, is the key part. So you just want to make sure that like this is like one of these axes is parallel to your seam. So you can figure out what because if it's not, then you're calculating the shear at some random angle and the normal force at some angle. But if you have it perfectly aligned with your thing, that'll show you exactly the forces that are occurring along that weld line. So there's different ways of. This will also become more clear on Thursday. So you can use 2D stress elements for 3D problems. You just have to be a little bit careful about how you use it, but they can be very useful.
But the idea is it would fail at the joint between the one part and the seam, not in the middle of the seam.
Right. Yeah. For this case, yes. Yeah. On Thursday, we're going to look at a problem with torsion, and that's a little bit different. But yeah, we'll talk with them. Okay. How's everybody doing? Kind of have answer-ish? Cool. This did come from a book, so this is right. Exactly. Yeah, so yeah, this kind of makes sense, everybody? Does the plug and chug make sense? Ish. Yeah, cool. All right. So we're gonna jump back real quick to the classic example. So I went out and calculated these values for 0 degrees, 25 degrees, and 45 degrees. So now we're kind of getting into, so basically so far we're able to transform a stress state from one angle to another angle, right? That's what we've covered so far. That makes sense. So now you guys are able to do any of these like basic fundamental stress transformation problems, which is cool. not hard. So now we're going to look at now we're kind of leading towards the failure theory thing, right? So where do you find, like, what angle at which do you find those maximum values for shear and normal stresses? That's kind of like the big thing leading towards failure theories. It's like what angle, you have to be able to find the right angle and what those maximum values are, right? So we're gonna take a closer look at the class example here, like I said. So like this is our given state of stress, right? So we have 1 KSI and nothing else, right? And then at 25 degrees is what you guys just calculated a minute ago. We have, basically the X prime is a little bit lower. We added a little bit of Y prime, and we also added a pretty good chunk of shear here. If you rotate it all the way to the 45-degree line, then these two values become equal, right? Because of the component thing, so you have like 2 45-degree vectors instead of a thing. So this makes sense. We also have a 1/2 KSI peak shear stress, and so in this example, it's pretty easy to like intuitively figure out what's going to be the maximum, right? Like you're never going to get more than 1 KSI because this is like literally the load divided by the area, and you're never going to get more than 1/2 KSI shear stress because there's no way to load this in a way where you can like pull more directly on that like parallel with the skewing action, right? So this is your peak shear stress, and this is your peak normal stress, but it's not always this clear. Yeah.
So in the uniaxial tension test, which seems like this is pretty similar to,
Yeah.
we
Kind of.
also had failure lines along the Luger lines or whatever, which are always at like 45 degrees in the dog zone. Is that the same thing here? Because those differential elements would have like max shear at 45 degrees across that face.
Exactly.
Very cool.
Yeah. Exactly. Yeah. Does this make sense? Cool.
What's the X prime, Y prime?
It is not indicated here, but it's I mean, this is the same example as before, so it's still using this stuff right here.
What's sigma?
Oh, that's the normal stress in the X prime and Y prime directions. So yeah, so think about X prime is along the X prime axis, or the X prime. So you're projecting normal stress along that direction.
I think that like classically, this is still valid, but traditionally, you can also see that as tau. Like, I think he's asking about the red sigma.
Oh, I may have just not corrected it correctly. Where is it?
Yeah, so like. the
Oh, yeah.
so
That's a
the bottom
typo.
row,
Yeah. Sorry. This is tau. Yeah.
It's supposed to be tau. Sometimes some texts will still do it in that direction.
Okay.
A lot of them will like switch to tau just to really delineate this is shear stress.
Yeah.
But technically this is still tau.
That's just the middle one.
Probably. Yep. All right, I'm gonna make a note of that to correct the typos. My bad, sorry. Yes, thank you for typo catching. Yeah, you've been good at type this semester already. What slide is this? This
You
is
gotta
21.
monitor.
I know.
Compliance check.
Yeah, good catch. Thank you. Cool. Yeah, so now we're gonna watch a little bit of this video. This video is really helpful for building like a little bit of intuition around this. We're not gonna watch the whole thing, but we're gonna watch a little subset of it. Yeah, efficient engineers, really good. I'm gonna rotate a little bit so I can see better. I'm not gonna play the audio yet. Okay, so basically the setup here is he gave a, oh my gosh, I hate this. There we go. So he gives this initial condition, right? So we have an initial condition of a stress state over there. And then he's going to rotate it. And as he does that, he's going to plot the normal stress in the X direction, or like whatever the current, thank you, the current X direction is, and then whatever the shear stress is at the same point. Does that make sense? Okay. So as it rotates, you can kind of see that relationship. There you go. So a couple important things to note about this. I actually think he's going to go into it right away. So like we just said, like I said earlier, this rotated 180 degrees, and that gave a full sweep of all the possible stress states, right? Because they're equivalent, rotating 180 degrees gets you back to the equivalent.
The graph of the normal stress is that like the direction of the y direction.
So this normal stress is not labeled here, but this normal stress is the sigma x. Sigma y isn't labeled, but it would be a similar swoop and different magnitude basically. And it also has a different phase shift, but you kind of see there's a phase shift right between the normal stress and the shear stress, which makes sense. Like if you go back to thinking back to the other example we had, when that weld seam was vertical, when our stress element was vertical, maybe there was no shear stress. So that was kind of like here, right? Because we had no shear stress, but a lot of normal stress. And then when we rotated it a little bit, we're kind of here in the middle somewhere, we have a little bit of both. And then when you rotate it to 45 degrees, we're at this point, right? So we have a little bit of normal stress somewhere in the middle, kind of somewhere. And then we have the shear stress, is our peak shear stress, right? And then, we can go on from there, but so that kind of makes sense. So, okay. I think he labels these real quick. Right. The stress state is not changing. The stress element and the normal and shear stresses are changing, but the overall state of stress in the part is not changing. Skip ahead a little bit. There you go. So you can see that the peaks between the normal stress is 90 degrees apart, which makes a ton of sense, right? Because we're rotating a square, and every time one of those faces lines up, like especially in our tension, every time one of those faces lines up with our tension force, that's going to be a peak. Same thing happens in no matter what load case you're talking about, or no matter what orientation or thing you're talking about, it's always going to be 90 degrees apart from between the peaks. If that makes sense. Anything else? So basically when those here we go. So when the shear stresses are 0, you're going to maximize your normal stresses, and at these points are called the principal stresses. So this is maybe the most important thing out of stress transformations is principal stress. This is going to be used later on. It's used some on FEA. I don't know, I've never done it in FEA, but it's definitely a thing. We'll get to that later, but
We use principal stress to get to calculate your bond stress.
right.
And Tresca and everything. Big fireworks glaring,
yes.
get out your highlighters.
So not enough emojis on this page. Yeah, this is super key though. And the cool thing about this is no matter what orientation you start with, given whatever, say we're dropped into the other example, we're dropped in at some weird angle, you can find the principal stresses by using these equations. You can find the angle that occurs in that equation, no matter what starting parameters you're given. And then by convention, the largest, whatever, so there's a plus or minus here, right? Whatever the larger one is going to be sigma 1, and then sigma 2 is going to be whatever the smaller one is. How's that feel? Make sense to everybody? Cool. Yeah. Big fireworks and things. Yeah. Cool. So I have you guys calculate it for that practice problem we have. So, this is some body, right? We don't know what angle this is. There could be a giant part. It's some weird angle around it. We don't know the context of this. We don't know anything about it, but we can find the principal stresses and what angle they occur at using this, if that makes sense. And there's going to be 2 solutions that satisfy this, right? Because it's a tangent, right? So there's 2 solutions that are 90 degrees apart that will satisfy this, and that will give you your 2 different theta values. Theta P is usually what it's called, theta P for the principal stresses. So there'll be one where maximum magnitude occurs at, and one where minor principal stress occurs.
From the previous slide, you said that sigma 1 is greater.
Sigma 1 is always greater than sigma 2, that's just by convention. What's that?
The minimum.
So yeah, if we go back to
Oh, wait, but that's like X and Y.
hold on. So in this case, this is sigma 1, right? Because it's your peak, and then this is sigma 2 because it's the smaller magnitude. So it doesn't matter, like, it doesn't matter which, like the plus and minus in that equation doesn't matter. That does not control the 1 or 2. Only the magnitude controls the 1 or 2. So you just got to calculate both and then figure out which one is which after that. Yeah.
I'm sorry, you probably already answered this, but with the sorry, the normal stress one, that would be like the adding those together, and whichever is bigger, the adding them, and then
Yeah, whichever one's bigger. So basically, you just the way like I've seen it in videos, the way I do it is you just like write the two things down, 1 plus 1 minus, or just you do it in calculator or whatever, and then whichever one is the larger magnitude, or sorry, not lag, whatever the larger value is 1. Yeah. So even if like that's it. Did Emily derive the transformation equations?
She did.
We started, I
Yeah, so. we
remember
started-
talking about it.
We started, I'm looking for my old notes
Yeah.
to find it, but we started with like just a standard triangle and then
Right.
she like drew it like on top of each other.
Mm.
And then like. I was still taking notes and like, after looking at this, it's really hard to read.
I was taking paper notes. I have no idea where those are now.
That's why I'm glad I got the right.
Yeah.
So like. She had started it where like we grab an element and then we rotate it and we have like X prime exactly as we did it. So I like your visualization a lot more.
Those are just to remove all of the clutter. It feels like people like make this a bit super overcomplicated, but I don't know.
Which
The
like,
derivation is good, but
yeah,
maybe not necessary for that.
we're not in that. That's the.
It's a
that's
2
another
credit class, yeah.
Yeah.
All right, everybody feel good about this? All right, so these are the answers I got. Nice. Yeah, so you can see that like our principal stress here. So like there's already a lot of stuff, like a lot of load going on here in this case. So you can see that we have a larger, like obviously it's a larger rate. This should definitely be larger than this, especially if you have shear stress. So while there's a shear stress, you're not going to be at your peak normal stress values, right? And so the kind of the general rule of thumb for figuring out which direction they go in, so the 2 ways of figuring out where these angles match up. So either you can plug it back into the original stress transformation equations. So you plug in your initial conditions and you plug in, like for example, this theta value, and then that will give you an output that should match one of these 2 values. The other way you can do it is that basically tells you like one of these will be at 29 degrees, one of these will be at 190 degrees. The other way you can do it is by kind of by intuition. So if you look at this right here, so go here. So I know. Okay, so right now we have this thing right here. And we have a shear, like a positive shear, right? So it looks like this. That's not right here. Right. And so the way like this is going to, like if talking about like strain, we're going to talk about this on Thursday a little bit, but there's this thing is like transforming stress, or sorry, transforming strain transformations are a thing. We'll get into that Thursday, but basically this is going to be working towards elongating it like this, right? So it's kind of parallelogramming it in that direction, or making it promising it, I guess. And so if you think about it, you're going to get your if you rotate your original orientation frame to make one of the faces line up with this axis right here, it's kind of your shear axis from your original thing. If you rotate your coordinate system this direction up like this, so align like this face more with this, so you're averaging more into this orientation. Sorry for drawing over itself sometimes, but if you align that shear, if you rotate basically, you rotate this whole thing towards that shear direction, you're going to increase your normal stress, right? Because you're unloading the shear and you're loading up that normal stress. Does that make sense? So basically you can kind of intuit that, you know, if you rotated this thing up 29 degrees, this larger value is going to get closer to that axis, which means you're going to get closer to your peak here. So that means that the 29 degree value is going to be for sigma 1 and then 119 degree value. Does that feel good? Does that make sense? Cool. So the other super key thing here, maybe a little bit less super key, but still pretty super key, is finding your maximum shear stress. So along with the principal stress, this is going to be basically, if your principal stress is how if your material fails in not shear, if it fails in tension, this is going to be the breaking point, right? If you're doing something that fails in shear, which is a lot of things, this is probably going to be your failure mode. So we'll talk about what more that means later on in like failure stuff, but this is very important for some things. Yeah, so similar kind of deal. You have this. So basically, there's two ways of calculating it. You can calculate your max in plane. So this is something that I have never ever seen a good visualization for in plane versus out of plane shear stress. Have you guys ever seen one? I've seen like a couple diagrams showing in failure theories, like visualizations of it, but I've never seen a good thing coming from stress transformations.
There is a video on plane stress
Yeah.
by a fission engineer that does like a somewhat good job, but it is confusing.
Yeah.
I'm gonna let Nathan talk, but
Yeah, I'm definitely open to
yeah,
getting to Carlos.
you're up, coach.
Yeah, so basically in all of the things I've ever seen, it has just been described as in plane and out of plane, and there's no explanation. Like if you Google it and look at up most things online, it just says in plane and out of plane, and it just goes right along, doesn't ever circle back to what that means at all. So I'm gonna do a little bit of that, and then I'm gonna see if I can figure out a better visualization for Thursday, for what that looks like. It's a little bit easier when you get into 3D stress elements and stuff like that. It's a little bit easier to visualize, and it's a lot easier to visualize when you're talking about Mohr circle, which we're also going to do Thursday. So it will become somewhat more clear. I'm going to see if I can make it a lot more clear, but to be determined. Right now, basically, there's the max shear stress in this plane that you're looking at, and there's also going to, but sometimes, depending on the case, there will be a shear stress that is greater out of that plane. So not in this normal XY plane. It could be in a different direction. So like, because basically all stress elements are 3D, where right now we're just ignoring the other axes. Does that make sense? But yeah, so basically out of plane might mean that, like the one visualization I did see that kind of made sense was if you had say you had like some piece of material like this, right? So some like flat plate. The visualization that I saw was kind of like this, right? Like this, right? So this is an example of an out of plane fracture. So basically it's something that's not necessarily happening on the same plane as your thing. So we'll leave it at that for now, and then we'll circle back. But basically the fundamental thing is that there are there's a max in plane and then potentially a max out of plane, and the max out of plane might be more than the max end plane. So if you just calculate the end plane stress, there might be another stress, there might be another shear stress that you're not accounting for that might fail. Yeah.
Which of those maxes in the plane should we use?
So yeah, so there's two different ways you can calculate it. If you've already calculated your principal stresses like we have for this equation, you can use the principal stresses here. If you haven't already calculated that, you can jump to what the max shear is by just plugging in your initial, like your whatever initial orientation values are here. Because you have your normal stresses and your shear. So yeah.
The other thing to notice, and like this will be hammered in on Thursday, if you go back to your principal stress equations, and you notice the second term of that in the equation is the tau max.
Yeah.
So
yeah.
That'll make sense on Thursday.
And then like before, that basically, if you take the negative reciprocal of the same equation we've used to find the angle of principal stress, and you get this because it's 90 degrees on, 45 degrees off. 45. Okay. Yeah, basically out of phase by 45 degrees. Yeah. That makes sense, everybody? Cool. All right. So we're gonna do the same thing again. We're gonna go back to our classical common practice problem. And you guys are going to calculate the max in plane, the max out of plane, which should be like 3 clicks in the calculator, and then what angle they occur at. Yeah. Angles they occur at. Oops.
The solutions were posted, they just weren't posted on the exam.
Oh, was it
looks like
updated
it's
assignment?
updated assignment, yeah. Oops.
Sweet. That'll be quite handy actually.
I like that, because only about half the class got it right. So.
Great.
I didn't
Yeah.
get it right.
Are we finding the tau max for like when it's rotated or on that like?
So ignore this 20 degrees. This 20 degrees doesn't matter. This is just ignore that 20 degrees. This is the max in any. You're looking for the max shear stress in any orientation.
Okay, oh,
Yeah.
it's using there.
Right.
Yeah, thank you.
Yeah. All right. So cool. Those are the values I got. That match up with what you guys got? Sweet. Excellent. Yeah, so if you note that 16 and 74 are, wait, hold on. Yeah, there should be out of phase by some amount. I don't know, I'm not gonna think about that too hard right now. All right, so yeah, so this is basically all of the really big fundamental things about stress transformation. There's a lot more like nuance and fine stuff and ways of using it that we'll get into on Thursday. But I kind of want to just leave it here for now, let this sink in and make sure this is like you guys have a really solid grounding in this. And this makes sense and is not like, this is not very hard. This is like, this kind of stuff is just plug and chug. It's like the really hard part is how to apply this to actual things. So we'll get to that. But for now, we're gonna leave it here and make sure this settles well. So one quick peek into what we're gonna work on Thursday. So 2D stress transformations and stress elements aren't like, like initially when you look at it, you might think that it's only good for like fictional 2D problems, but it can actually be really useful for 3D problems, because it turns out when you have a free surface, right, there's not going to be any normal stress in the plane that's normal to that surface, right? So there's nothing pulling on that free floating face. So you can actually apply it to the edges of things for surfaces. So one of the problems we're going to look at on Thursday, we'll tie this together with that. Like if you're twisting a beam, like twisting a chalk, like Carlos did on the very first day, when you're twisting a chalk, it breaks in the 45-degree angle. We'll see why that is and it has to do with this. And then also obviously for a flat plate that is just, it has some thickness with no loads like on either side of that flat plate. You can also use it for that, of course. Yeah. And then we're also going to peek at 3D stress transformations because of course, adding a third dimension makes it more exciting, more complicated. So yeah, there are people do 3D stress transformations by hand, but
This is disgusting. It's supposed to look disgusting.
Yes.
but We're not doing this by hand.
no, we're going to show you the cheat code.
Yeah.
It's going to be fun. But yeah. Yeah, so I also put a big list of resources here. Some of these I used to like, this is the stuff that I found useful when I was relearning it so I could teach it. Yeah, so if you guys want to like ever need to like go back and reference some of this, like all the things, I tried to put like a description of what each of these things are. This is like a super in-depth, like hard to read, super math nerdy version of it. There's a couple like really basics, like examples of it stated different ways. So whatever style you like to learn, there's probably a solution here that will fit that. And then here's that formula she was talking about. So this is all the equations from class today that could be useful. Yeah, so we're going to chat real quick about Thursday. So you might have seen Katie's Canvas update. So on Thursday, the plan is we're going to be doing kind of like a gallery walk style thing. So if anybody of you taken like a Tim Sauter class, like tell a story, something like that. Basically the idea is if you guys want, or please are telling you to please bring a screenshot or a physical copy, some artifact of the medium you've chosen for your reference resource, and an option that you looked into and kind of like tested a little bit, but decided not to. Reference resource is your
what is a reference resource?
Reference resource is your final project thing. So originally due today, but we didn't remind you on Thursday. Now due this coming Thursday, next class, we would like you guys to, there's a thing on it on Canvas. We'd like you guys to look into, Katie, you're trying to talk. I think I have you muted. Are you there, Katie?
Yeah, I'm here.
The audio is really weird
Yeah.
on this. It might
Okay.
be more useful just
Anyway.
on Colin's laptop.
I got some. Oh. I better mute. Cool. All right. Let's see if I get. All right, should be. Katie, if you want to chime
Can
in,
you hear me?
maybe it'll work.
Hello?
Did you change the audio in the Zoom thing? 'Cause sometimes you have to change it to be the speaker
Yeah.
system.
Put in my internal speakers. Okay, how about now, Katie?
Hello?
That works. Yep.
Okay, you can hear me?
Yes.
Awesome. Do you want me to chime in about this? I don't know how much you said.
Oh, I was muted. Dang it. Yeah, you're welcome to if you want, but I like re-explain the reference resource, and then explain the gallery walk.
Yeah, yeah. I mean, just to add in, I think the point of this is mostly just so that you can start thinking about this project, start like letting it percolate in your head a little bit. We don't want this to be a big stressor. We just want this to kind of help you organize the information that we're providing you so that in the future you will be able to look back at this and easily find your resources or reference something, hence the name reference resource, that will help you with anything you encounter in the future. So no worries if you choose something this Thursday and you start filling it out for in the future and you realize that it doesn't really provide the structure that you want, you can totally change. This is just to kind of help you get started. And then we'll be assigning another small assignment in the future where you start adding on different topics. We'll start with the beam bending and then go from there with adding in any references and information that you want to capture from what you learned in the class. Canvas in the future for more of those types of assignments. We'll usually try to line it up with the other homeworks as well, and we'll add in just like a reminder to check that out. And it should be, yeah, all on Canvas.
Yeah, I'm screen sharing the check-in assignment that you made right now. So
Yes,
yeah,
Yeah,
it's here.
don't-
on
yeah.
Monday.
it should be all set there.
Cool.
Yeah,
Thank you, Katie.
thank you.
All right. And one more thing, a TA hours check-in. Yeah, so we want to know if you guys are using hours, like, are they at good times for you? Does it make sense? Yeah, so just, yeah, please let us know if this works.
Yeah, just be brutally honest.
Yeah.
Like, I mean, if you realistically think like you're not gonna work.
Yeah.
Oh, yes.
Yeah, this is a small class now, and there's like a lot of TAs and us to go around. So yeah, if it's at a bad time for you guys, we want to know and make it a good time, because that's the whole point. That way the CAs can get paid and also have meaningful hours at the same time. Winning combination.
We want CAs.
Woohoo! All right. Yeah, so please go fill this out if you aren't already.
I do one last final thing.
Yeah.
Do you have MATLAB on the computer?
Yeah.
It might be like, go ahead, but I think it's cool. And when I first saw it, and we're not asking you guys to do this on your homework. If you're in Mech Solids, you will do this on your homework. But just like kind of a sneak peek to this.
Let me reconfigure her screen. Oh my God. I gotta find MATLAB. There we go. Yay. I hope our 2020A is good enough for you.
Oh, that's okay.
Last time I used it with signals.
Yeah, how do I get an actual, instead of command window, how do I get the workspace out? Oh,
Do what?
instead of like the command window, just the. Oh my God, what's it called?
Like this?
There we go. Oh, there we are. Yay. Okay, so I'm just gonna look at my slides. This is off rip, but I think it's cool.
Do it.
The first time I saw this, I was like, that's nutty. But I'm going to take this problem on slide 24. So if you guys want to pull that up. We have a stress element I'm just kind of writing this for my own sake. We have 700 PSI in the sigma Y direction, and we have 1200 in the sigma X direction with shear stress of 400 PSI. Going back to like representing this as a tensor, it's not a matrix, it's a stress tensor. What was the symbol for it? There's a symbol for this. Isn't it just E? Tensor? Or is it T? I think this is wrong, but I'm just gonna make it. What's up? I don't know what it is, and I'm not gonna pretend, so I'm just gonna do a star. Just someone- There we go. Thank you. Oh, that's right. Yeah. This guy. Can you guys see this over here?
I have never seen that before.
Yeah.
Not for this.
So
Yeah, in square brackets too.
going back to this, you have sigma X, tau XY, tau technically YX, but we're saying they're equivalent, and sigma Y here. I'm just gonna put this up real fast so you guys can see this again. Also, if you go back to one of the earlier slides, like this is available right there. Can you guys, no. Just to see what that looks like. If I go to my MATLAB script and I make that, represent that as a matrix, I'm just gonna call that stress equals 1200, 400 colon 400, 700. And again, just that 1200 is sigma X, shear stress, and then sigma Y. So my shear normal stresses are on my diagonal. If I do that, that runs, I have my matrix pop out right there. If I take the eigenvalues of that, whoa. And then I go back to, so I have like 478.
Almost as if it's all.
200 something. Whoa. Who wants to have a guess of what the eigenvector would be? Yeah. So that's it. I thought that was cool as hell the first time we did that. You guys will get a far better understanding in Chris Lee's next solids on why that exists, but that's also a super powerful tool that you have at your disposal. Yeah. So I can do my best to try to explain this, but Jeff didn't really spend too much time other than just going like, eh.
Do it.
Yeah. Yeah. What's up?
You talked about that matrix.
Yeah, absolutely. So, fuck projectors. We're going back to chalkboards. So, I'm gonna call it a matrix